As a warm-up and introduction how to solve linear programs, we first look at the one-dimensional case of a linear program. In this variant, or in this special case, we have only one unknown. So we have only x1, which is the unknown. We want to minimize c1 times x1 up to some constraints such as ai1 times x1 less than equal bi. Try to pause this video and try to see if you can actually solve this. This is not too difficult, but it requires that you think a little bit about this to become comfortable with how this is formulated. Now I'll continue with the video and I'll tell you how we can solve this. So one way to have an intuition about this problem is to consider all the real numbers, the set of all real numbers, let's say this axis. This can represent all possible values for x1. x1 is a real number, so it could be anywhere on this line. So in other words, this line represents all possible values of x1. Now let's look at the first constraint. The first constraint says a11 times x1 less than equal b1. And remember that all these below variables are known. They're given to me at the input. So for example, this could be 4 times x1 less than equal 8. Okay. Of course, if we have such an inequality, then we can deduce from this that x1 is less than equal 2. The only thing we have to pay attention is the sign of this coefficient here. So if I had instead minus 2x1 less than equal 10, right? From this I can deduce that by dividing by minus 2 that x1 is bigger than equal minus 5. So basically the only thing we need to pay attention is that if this guy is negative, then we have to flip the inequality. Okay, and essentially this is what explained. From this we can get that x1 is less than equal b1 divided by a11 if this is positive, and the other way around if it is negative. If a11 is 0, we have another special case. Then this left hand side is completely 0. Then if b1 is a negative number, then this is impossible. In other words, it's impossible to satisfy this constraint. But if it is not negative, then it's always satisfied, so we can just ignore it. In general, this can be represented by forbidding a particular half of this line. So let's look at this case. In this case, x1 is supposed to be less than or equal to b1 divided by a11. b1 divided by a11 will be a number, let's say at this position. And this inequality forbids this right hand side. x1 cannot be here because this inequality says x1 should be smaller than this value. On the other hand, if I had this other case, then this inequality will forbid the other half. It would forbid this side because it says x1 should be bigger. So x1 should be here, that means that side is forbidden. But that's only the effect of considering one inequality. The remaining inequalities have a similar effect, except that the effect of forbidding pieces of this line is cumulative. If something is forbidden once, then it's forever forbidden. So in other words, once we add all the forbidden regions, these entire piece is forbidden, this entire piece is forbidden, then if we're lucky, then there is a little piece of the real line that is not forbidden. That is called the feasible region. The feasible region, since it's not forbidden, by definition satisfies all of these constraints. Because if it did not satisfy one of them, then it would have marked as forbidden and it would be marked red. And forbidden region will have kind of an interval shape. In other words, when we forbid a piece of this line, we pick a line, we pick a point, and we either forbid the entire thing to the left or the entire thing to the right. If I union all of them, then it will be something like this, and so therefore the part that is not inside the forbidden region will look like an interval. Another way of seeing this is, okay, before seeing that, let's look at the objective value. So now everything here is feasible. But what is it that we want to find? We want to find the minimum of this function. What is the value of x1 inside this region that minimizes c1 times x1? Again, here we have a number of cases. If c1 is positive, then we want to minimize x1 times, we just want to minimize x1. Because if c1 is positive, minimizing this is the same as minimizing x1. So that means we're looking, this is the answer. This left endpoint of this feasible region is the answer. If C1 is negative, then this is minimized by maximizing x. We just get a number that is more negative. So therefore we want to maximize x1. So therefore we get this other endpoint. If C1 is 0, then that's a special case. It means that any point inside this feasible region will minimize this function because the value of the function is just always 0. So we have a number of possible cases when we look at all these constraints. The LP could be infeasible. It means that the forbidden regions in overall forbid the entire real line. There is no value of x1 that satisfies all these constraints. This is called as infeasible. It could be unbounded. For example, let's say if all the A1s are negative, then you're forbidding, let's say, the right half side of some point. And minimizing x1, the answer could be minus infinity. So unbounded means that x1 is either minus infinity or plus infinity. It is there is no real number that minimizes. For every real number, we can find another real number that achieves a smaller value. It could be feasible, and so that's the normal case that we discussed. And feasible has a special case that's a degenerate solution, in which case C1 is 0. In other words, every point inside this region is a potential value that minimizes the function C1 times x1. So what is the running time of this algorithm? This algorithm is linear because the only thing we need to figure out is essentially take the maximum and the minimum of a bunch of values. If I go back here, when this coefficient a is positive, then we're obtaining an upper bound for x. So therefore we just find the maximum of all these values where x1 is positive and minimum of all these values when a1 is negative. So this can be solved by a simple loop where you find minimum and maximum. We're going to do some in-class exercises with this so that this is so you can really understand this. But the algorithm is very simple. You just for loop through these constraints and find the minimum and maximum of bi divided by aii, and take into account the sign of ai1, and that is the one-dimensional